Hello everyone, welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have these lecture slides, you may refer to my GitHub page at this given link. So from last few lectures, we were discussing the non-parametric estimation techniques where we have estimated the probability densities of a set of data samples using the different approaches like windowing technique or histogram based technique. So here we are going to discuss a new type of classifier, which is a nearest neighbor classifier, where we need not to estimate the class conditional densities. So here we have seen in last few lectures, in last lectures we have seen. So whatever we have studied till now, we have been using the Bayesian classifier that make decision according to the posterior probabilities, and we have discussed the parametric and non-parametric methods to estimate the probabilities using the training data samples. So here we are going to study a new technique that use the training data to learn the classifier directly without estimating any probabilistic structure. That means we need not to estimate the class conditional densities as we did in the Bayesian classifier. Okay, that means we need not to consider parametric or non-parametric methods to estimate the class conditional densities. So in this lecture, we will study the k nearest neighbor classifiers, which uses the training data to learn the classifier. However, we have other classifiers as well, like linear discriminant functions and support vector machines. So, but in this lecture, our focus will be on the k nearest neighbor classifier. So, let us consider we have a set of data samples, okay, that is the training data set, and we have n number of data samples in that set. That means we have n number of labeled training data samples. Okay, then we will use our nearest neighbor classifier to assign a test point x, okay, and that test point x will be assigned to the class, okay, which will be closest neighbor in D. That means we will compute the distance of a test sample, okay, test data sample in the feature space. We will compute the distance from each training data samples. That means distance between test data sample and all the training data samples, and we will select the training data sample which is closest to this test data samples, and the level associated with that training data samples will be the level of this test data sample. Okay, so here we define the closeness, okay, using the distance function, and that we will study in this lecture. What are the different distance function we have? And for the given distance function, the nearest neighbor classifier partition the feature space into cells consisting of all points closer to given training points than to any other training points. What does it mean? Suppose in space we have number of training data samples. Suppose these are the data samples. Okay, so here if we will consider a normal nearest neighbor classifier, that means we are not considering k nearest neighbor classifier, only the nearest neighbor classifier, or you can say that k equal to 1. Okay, that means it will consider only the nearest sample. Okay, so in that case, this nearest neighbor classifier partition the feature space into number of cells. So how it will partition? The perpendicular bisector of these 2 points will be this. Okay, perpendicular bisector of these two will be this. So in this way, we define the perpendicular bisectors, okay, in such a way that our feature samples will be defined with some region, okay, and that region is called cells. So this type of diagram we can have in two-dimensional feature space, we can have in the d-dimensional feature space as well. It depends on that in which dimensional space we are working. So here, if we are in two-dimensional feature space, then we can have the cells like this, where the gray shows the cells corresponding to the class 1 and the white cells shows the region corresponds to class 2. So in the same way, we can have the three-dimensional feature space. So basically this diagram is called Voronoi tessellation, okay, where we define the regions associated with that sample. Okay, that means it will create number of cells associated with each data samples, whether it belongs to class 1 or class 2. So suppose we have one problem, and so what will be the Voronoi tessellation for this set of feature vectors? That means the problem is saying that consider the following set of 7 two-dimensional feature vectors. So x1, x2, x3, x4, x5, x6, x7 are given, where x1, x2, x3 are from class 1 and x4, x5, x6, x7 are from class 2. Then we need to sketch the decision boundary resulting from nearest neighborhood. So once we will define the Voronoi tessellation, then that will be our decision boundary, okay, resulting decision boundary. So let us solve this problem. So here the problem is given, okay. So let us draw the points, okay, in this space. Suppose this is our 0, 0, okay, and this is 1, 2, 3, 4. This is -1, -2, -3, -4. Okay. Similarly, here also we can label the axis. Okay. So now let us draw these points. So 1, 0. This is 1 and 0. So this is the one sample from class 1. 0, 1, 0, 1. This is another sample from class 1, and 0, -1. So here this is 0, -1. So this is the sample from class 1. So I can, this is class 1. Okay. Now we can have the sample from the class 2, and that is 0, 0, then 0, 2, then 0, -2, then -2, 0. Okay. So here we can find the bisector of two here. So here we can find the bisector of two dissimilar data samples in the feature space. So suppose here this one and this one, the two samples belong to different class. That means we have to define a boundary, okay, and that will be the the perpendicular bisector when the two samples will be from two different class. Okay. So here these two samples are from different class. So let me draw. So this is our perpendicular bisector. Okay. So basically here we have to find all pair of dissimilar samples. That means all pair of samples from the different class. That means one sample will be one class and another sample will be from different class. So this one and this one. So again we have to consider the perpendicular. So here it will be, this will be our, okay. So in this case as well, okay. So we have how many pairs? Let me consider all. So here we have one pair, okay. Here we have one pair. This is another pair. This is another pair. This is another pair. Okay. This is also one pair. And do we have any other pair? This is another pair. This is another pair. Okay. So that means we have to consider all the pairs. Okay. So here how many? 4, 5, 6, 7. Okay. That means we will have the 7 straight lines. Okay. So here we have drawn 3 straight lines. Next, this will be our perpendicular. Okay. That means bisector of the line joining these two dissimilar data samples. Next, this is our dissimilar. Okay. Then these two are dissimilar as well. So here this will be our vertical axis. Okay. This side also. Okay. This will be our one boundary. This will be one boundary. Okay. So here now you can notice there is some visualization that we have drawn all the lines. So how many lines we have drawn? 1, 2, 3, 4, 5, 6, 7, 8. We should count from the starting, then it will be good. Okay. So here just I'm drawing first what I am visualizing here. So here, not this one. Here, this is the line. Okay. So when we will have this decision boundary, okay, then this side will be our class 2, okay, and this side will be our class 1, okay. So this is the decision boundary that we can sketch, okay. So what is the nearest neighbor algorithm? So algorithm says that we have to store all the labeled training data samples, and so this is the basic learning algorithm. In learning algorithm, nothing we have to do, just we have to store the labeled training data samples in the memory, and then we have to predict. And how we will predict? To classify a new example X by finding the training sample, okay, that means we will compute the nearest training sample with the label that is nearest to X, and whatever the label is associated with that nearest training sample, that label will be assigned to new example X, okay. So this is the learning algorithm for nearest neighbor algorithm, okay. So this nearest neighbor algorithm will consider only only it will consider the closest sample, that means k equal to 1, but we can consider the number of samples, that means number of neighbors to the test sample. So that's why it is called k nearest neighbor classifier. So here, to classify a new input feature vector X, examine the k closest training data points to X and assign the object to the most frequently occurring class, okay. So suppose we have set of training data samples, okay, and we will compute the distance of test data sample from all the training data samples in the feature space. Then we will find the k closest training data points, and there from that set we will find that what is the majority of the data sample belongs to which class. That means what is the majority of the class. That means suppose here we have set of data samples, training samples and test training data samples from the two different class. Red is from class 1 and blue is from class 2, and this black is our test data sample. So we can have a nearest neighbor that we can consider. So suppose we are considering the k equal to 5. So outer circle includes 5 number of training data samples, and among those 5 data samples, 1 is from class 2 and 4 is from class 1. So that means this unknown data sample X will be assigned to class 1, okay. So we can consider k equal to 2 as well, okay. So we can have the different value of k. So a very common choice is 2, 3 and 5, okay. In many applications we usually use 3 and 5, but it can be any value. So here some inference about the k nearest neighbor classifier, that it is computational complexity of the nearest neighbor algorithm both in space, that means with respect to storage, and the time, that means where it will search the number of samples, has received a great deal of the analysis, okay, because it takes lots of time, computationally expensive. So in this algorithm, people have given lots of effort to come up with a very computationally efficient algorithm, but it will does the same thing, okay. And in the most straightforward approach, we inspect each stored training point one by one and calculate the distance to X, okay, and keep a list of the k closest ones, okay. So that is the straightforward approach that we have just done, okay. That is the straightforward approach, and there are some parallel implementation and algorithm technique for reducing the computational load in the nearest neighbor searches, okay. So this much for k nearest neighbor classifier. Now let us discuss some distance functions that we can use to compute the nearest neighbor in the feature space. And this distance function will be also very useful when we will deal with the clustering, that is the unsupervised learning. There also we compute the distance to find the similarity between the two feature vectors. Okay, so let us discuss the distance functions. The nearest neighbor classifier relies on metric or a distance function between the points. Okay, and how the distance between the points is defined. So here we can define that we have 3 points, suppose. That means this is the some properties of the distance or some metric. So suppose we have a metric, okay, where we have to compute distance or some metric between the 2 points, then must satisfy the following property. The first property is non-negativity. That means the metric or distance cannot be negative. So if we will compute the distance between any 2 points, the distance can be 0, but it cannot be negative. Okay, so it will be always greater than or equal to 0. Next property is reflexivity, and it says that if dxy is 0, if and only if x equal to y. That means the distance will be 0 if and only if we are talking about the same point. That means x and y will be at the same point. Then distance or that metric will be 0. Other property is symmetric. That means if we compute the distance between xy or yx, it will be same. Okay, that is the symmetry. Another property is that triangle inequality property. That means if we have 3 points, okay, suppose this is x, this is y, and this is z, then the distance between xy, distance between yz, okay, and the distance between xz, then our triangle inequality property says that the sum of two distance will be greater than or equal to the third distance, okay, which forms the triangle. And equal will hold only when all the 3 points will be collinear. Okay, and here special case is that if the second property is not satisfied, then this distance metric will be called as pseudometric. Okay, so a very general class of metric for d-dimensional pattern is the Minkowski metric. This is very famous distance metric, which is Minkowski matrix, and many metrics came from this expression only. So here this is also called the LP norm, and which is given by this expression. And if in this expression p will be equal to 2, then it will give us the Euclidean distance, and that is called the L2 norm. Okay, so here just we can put p equal to 2, and the expression will be for the L2 norm, and that is basically our Euclidean distance. So here we can remember that Euclidean distance was x1 minus y1 square plus x2 minus y2 square plus, and it is xd minus yd square if we are dealing with d-dimensional feature vector, and this is under square root. Okay, we can have p equal to 1, and that is called the Manhattan distance or city block distance. You might have heard this distance in image processing. Okay, so this is called the city block distance. Here we can have p equal to infinity, and if we will consider p equal to infinite, then This is the maximum of the distances along the individual coordinate system. So suppose we have the d-dimensional feature space, and then we will compute the distance along each dimension, and we will select the distance which having the maximum value. Okay, and that is called the L infinite norm. Okay, that means P will be infinite. Okay, so you can understand this one using this diagram, where this green color shows the locus, or that means the distance. Okay, that means on this path the distance will be same. Suppose we are dealing with the P1. So P1 says that it is basically the city block distance. So if we want to reach at this position, okay, then it will come here and then it will go here. Okay, so if we want to reach here, then it will be here and then here. So the summation of all the distance, it will be on a line. Okay, similarly, if we have P equal to 2, then that will be our Euclidean distance, and you know that Euclidean distance is our circular. Okay, because our equation is x1 minus y1 square plus x2 minus y2 square and square root. So this is d, and if you will convert it to the circle equation, then it will be d square, so radius square equal to x minus, so you can consider it is a mu. Okay, so if the center y1 y2 will be 0, then x square plus x2 square, that means x1 square plus x2 square equal to d square. So this is the equation of this circle. Okay, and this will be our P equal to infinite. Clear? So this distance function is very important here in many different applications. So here we have understand how to compute the distances. Okay, however, we can, whenever we are dealing with the feature vectors, then sometimes we normalize the feature vectors. That means maybe at one dimension the value will be very high, and on the another dimension value will be very less. That means the variance of the values on one axis will be very high, and variance on the another axis will be very low. Okay, so we should be careful about scaling of the coordinate axis when we compute these matrices. Okay, when there is a great difference in the range of data along different axes. Okay, here different axes means what? The different dimensionality of the feature vector. In multi-dimensional space, these matrices implicitly assign more weighting to the feature with large range than those with small range. Okay, so we have to normalize the feature vectors. Okay, so feature normalization can be used to approximately equalize range of features and make them have approximately the same effect in the distance computation. Okay, so here we have different normalization techniques. Okay, the first one is mean max normalization. So if we have set of feature vectors, then we can compute the mean value. Okay, that is a minimum value of that feature vector, and also we can compute the maximum value of the feature vector, and then each feature vector can be normalized using the mean and max, so that our value will be in the range of 0 to 1. Okay, another approach is called standardization. Okay, or it is also called linear scaling to unit variance. That means it will be zero mean, unit variance. That means along all axes, the value will be zero centered and the variance will be unity. Okay. So here we will compute the mean value, okay, of all the feature vectors, and we will compute the variance. Okay. And already you know the expression to compute these, okay, that we studied in the feature extraction. Okay. Then we will compute the normalized or standardized the data samples feature vectors using this expression. Okay. So this much for this lecture. I hope I am clear to you, and if you have any doubt, you can ask in the comment section. Thank you.